4, 3, 2, 1.
On October 13th, the Starship, then the most powerful rocket ever built, made its 5th test flight in what is the most impressive and most successful flight so far. Both stages landed successfully as planned. This Colossus, which is developed by SpaceX, aims to make humanity a multiplanetary species. In other words, with the ability to explore and even inhabit other planets and moons within the solar system. It weighs about 370 tons empty and up to 5,000 tons fully fueled. It is 121 meters tall and 9 meters in diameter, composed of 2 separable and fully reusable stages. The first stage, called Super Heavy, contains 33 Raptor engines, which effectively lift the vehicle off the ground and carry it up to 70 kilometers in altitude. The second stage, right above, called Starship, can carry up to 150 tons of cargo and, in the near future, will land on Mars and other planets. It can carry up to 100 people and has 6 engines. To give you an idea of the power of this giant, during liftoff, the 33 engines of Super Heavy deliver a combined power of 76 meganewtons, or 7,600 tons of force. This is not only more powerful than the Saturn V, which delivered 35 meganewtons, but it's equivalent to the same power as 73 Boeing 777s at maximum power, or 146 Boeing 777 engines combined. Assuming the rocket is 121 meters tall and that the exhaust plume from the Raptor engines was about 1.5 times the size of the rocket, one can conclude that the exhaust plume was about 181 meters long, 181 meters of pure fire. But the most impressive part of Starship's 5th test flight was definitely the landing moment. When attempting the impossible and unthinkable landing of the Super Heavy, that is, the rocket's first stage, back at the launch complex at Starbase where it was launched from. How was this landing possible? The rocket risked missing the target and hitting the tower, causing a huge explosion. What would happen if the engines didn't ignite on the return? Well, to begin with, the Super Heavy features a design that doesn't include landing legs, just like its older brother, Falcon 9. This was done to reduce the total weight of the booster and consequently allow it to carry more payload into space. To give you an idea, each of the 4 landing legs on the Falcon 9, which are made of composite materials, weighs 500 kilograms. There are 4 totaling about 2 tons. Just in landing legs, by not including landing legs in the design of the Super Heavy, which is much more colossal. SpaceX saved about 14 tons in weight, which would be just from the landing legs according to estimates and according to the mass of the booster itself. That said then, let's go to the 4 fundamental systems that made the landing possible and successful. The first is the thrust vector control system on the Super Heavy's 3 central Raptor engines. The base of the Super Heavy is made up of 33 Raptor engines divided into 3 rings, of which the engines in the 2 innermost rings are used for the landing stage. Specifically, with the ignition of both rings for the initial deceleration maneuver, and later, only the inner ring containing the 3 Raptors remains for the final landing phase. The second fundamental system for the landing of the Super Heavy is the reaction control system, or reaction control system. It is composed of small thrusters strategically positioned around the outside of the vehicle. They release controlled bursts of compressed nitrogen to maneuver the booster along different axes, namely roll, yaw, and pitch. Along with them, the grid fins, or lattice fins, are an aerodynamic component that works by altering the airflow passing through them and, consequently, maneuvering the booster. They work together with a reaction control system after the Starship separation phase, and together, they allow for fine and precise adjustments in maneuvers all the way to landing. These grid fins, of which there are 4 on the Super Heavy, are made of titanium, and each one weighs about 1 ton and 360 kilograms, and they are approximately 5 meters long. The third fundamental system is the autonomous flight software, or autonomous flight software. SpaceX uses an advanced autonomous flight control system, which continuously adjusts the trajectory of the Super Heavy based on real-time data, keeping the booster on course. The software processes data from various onboard sensors, such as accelerometers, inclinometers, gyroscopes, global positioning system receivers, among dozens of others. Then it sends instructions to the reaction control system grid fins, and especially the engine's thrust vector control system for precise control. And the fourth and last fundamental system is tower orbital and integration, called the Orbital Launch and Integration Tower, or Orbital Launch and Integration Tower, located at Starbase, which contains the arms that actually catch the booster. This is known as Mechazilla. This tower both catches the rocket in the air and integrates the two stages on top of each other when there is a flight, or also when tests are to be carried out with the vehicles. This tower stands just over 146 meters tall. Once we know some of the critical systems that make the Super Heavy's landing possible, let's understand the rocket's return flight profile to Earth. Remember that what matters to us is only what happens after the separation of the two stages. In other words, the events that occur from 2 minutes and 30 seconds into the flight to 2 minutes and 32 seconds into the flight. The grid fins move and enter a specific angle, followed by the shutdown of 30 engines from the two outer rings. This phase, called hot staging, ignites the second stage engines before separation. This allows for enough relative velocity for the two stages to separate. The grid fins move so gases from the engines above pass through and help push the rocket sideways. The next phase is one of the most important and is called the boost back burn. It basically consists of canceling the rocket's horizontal velocity. But let's understand it better. If we could see the Starship's trajectory from another angle, this would be the path taken up to the moment of stage separation. In other words, besides going up vertically at a certain point, the rocket started to tilt toward the horizon. This means that besides the rocket having vertical speed, in other words, going upward, it also has a certain amount of lateral movement. However, for the rocket to return to the starbase where it was launched from, two things are necessary. First, the rocket makes a 180-degree turn so it points opposite its original direction. And the second thing is that the rocket needs to fire its engines to cancel out its horizontal velocity. This way, instead of following a full ballistic path and landing in the ocean, it can return to the starbase. That's why this maneuver is called boost back burn, which means a return burn. It starts at around 2 minutes and 45 seconds and ends at around 3 minutes and 40 seconds, so it lasts about 55 seconds in total, more or less. At that moment, the broadcast announces Tori is ready for the booster.
So we saw a reaction, so that was one of the criteria we were expecting.
Indicating that various systems were checked, she was able to receive a booster. This seems like simple information, but actually it's quite complex and critical. During Starship's 3-minute flight, thousands of criteria will have to be met. Both the vehicle and Tori's systems are in excellent health and fully operational. So that then, a manual command could be sent by the mission director for the Super Heavy to head toward Tori at Starbase. If a problem was found in either the Super Heavy or Tori hardware, the director would not issue the manual command. The Super Heavy would follow its usual descent and controlled sea landing in the Gulf of Mexico. If no problem was detected, as there really wasn't, then the director would send a manual command to the Super Heavy. so that the boost back burn maneuver would be performed aiming at Tori as the target. After the boost back burn is completed, with the help of the reaction control system, the booster performs another 180-degree flip, now positioning itself correctly for re-entry. Now, traveling at over 4,000 kilometers per hour in controlled freefall, a key safety configuration becomes crucial. The booster falls at an angle, not perfectly straight. This is done so that the body of the booster generates a bit of lift and helps guide it to the landing site. This maneuver also slows the booster's terminal fall velocity by creating drag at an angle, preventing excessive acceleration. During this entire descent phase, the grid fins, which are electrically actuated, move, making small corrections to keep the rocket on the correct trajectory, which, by the way, ends with the rocket falling at some point, many meters away from Tori. This is even more clearly visible when seen from other angles. This descent profile intentionally has the Super Heavy aim outside Tori for safety. SpaceX does this to ensure that in case the Super Heavy's engines don't ignite due to some failure, the rocket will maintain its trajectory and impact somewhere on the ground, far away from Tori, thus avoiding damage to the structure. This failure already occurred with Falcon 9, which follows the same descent profile and targets a point outside the landing zone. This allowed the rocket, even though it failed, to land safely in the sea and not compromise the structure of the landing zone. In the final moments of the descent, around 6 minutes and 30 seconds, 13 Raptor engines are ignited to slow the rocket from supersonic to subsonic speed. And then 10 engines are shut down, leaving only 3 that perform the correction maneuver. And effectively, they bring the rocket to Tori, where the arms of the Mechazilla mechanism close precisely to catch the rocket. The videos show that this correction maneuver shifts the rocket's trajectory from a precise landing far from Tori to landing on Tori. It's of great size. It's worth noting that there are 2 legs on the Super Heavy that actually make contact with the arms of the Mechazilla mechanism. The rocket is supported entirely by these 2 contact points. It's also worth noting that just moments before landing, the deluge system, which pours large amounts of water at the base of the launch pad to reduce the heat and noise generated by the engines. Raptor during launches is activated, probably in an attempt by SpaceX to mitigate possible damage to the platform. It was a unique, majestic, and successful landing on the very first attempt. This will definitely become routine in future launches, and the technique will be improved more and more. But there are a lot of technical things that aren't public knowledge and that went unnoticed by many people during this first successful landing attempt. And let's start analyzing them. There's a concept called suicide burn, and to understand it better, we need to understand how the power variation of rocket engines works. Unlike other engines in the world, rocket engines have an ideal operating zone. Below that, they just shut off. This zone where they already shut off is around 40% power and below. In other words, the power can vary anywhere from 100% down to 40%. Below that, they just shut off and stop working. The ignition of the 13 engines during the final descent is timed to occur precisely at the right moment, not before or after the ideal point. Then 10 engines shut down, since they were only for quickly slowing the booster. And only 3 engines remain, which are needed for the final stage of landing and for making all the necessary trajectory corrections. According to the rocket's own design criteria, these 3 remaining engines continuously adjust their power to ensure that the rocket lands on the platform at the lowest possible speed and as smoothly as possible. If the Super Heavy is too high or too far from the platform, when only these 3 engines are left, due to the thrust-to-weight ratio of the engines, which is greater than the weight of the rocket, this will cause the rocket's speed to reach 0, and it will start to rise again before it can land on the platform. Even if the engines are operating at the lowest possible power due to the thrust-to-weight ratio. And what if the Super Heavy is very low and close to the platform when only these 3 engines are left? It might not be able to slow down in time and end up landing at too high a speed, causing an explosion. That's why this maneuver must happen at the exact right time. And that's why it's called a suicide burn, although it's not publicly known whether the Super Heavy uses this suicide burn maneuver or not. Another aspect to consider is after the boost back burn maneuver. With this satellite image from Ryan Hansen Space Renders, which shows the tower where the landing took place in the upper left corner, and the green area is the estimated probable zone where the Super Heavy was aiming during its entire descent back for landing. This is the probable area where it would hit the ground if its engines didn't ignite due to some failure. You can see that it's a practically deserted area and far enough away so that debris from a possible rocket explosion wouldn't hit any critical infrastructure nearby. And if no problems occurred and the engine started and worked as expected, the rocket would then correct its trajectory and head toward the tower. Another point to consider is the rocket being captured by the Mechazilla mechanism. It's important to remember that the Mechazilla is a capture system designed to operate autonomously and is capable of capturing, lifting, and lowering rockets. The arms of this mechanism can automatically and individually adjust their position, timing, and force to catch the rocket precisely, responding in real time to any small misalignments. That said, as the Super Heavy approached the tower, precise data about its position, speed, and the likely landing spot were transmitted by telemetry to the Mission Control Center. This information allowed the Mechazilla to adjust its arms to better intercept and catch the rocket, since it could be slightly off the ideal capture point. In this video, you can see that the left arm is the first to start moving, followed by the right one closing in and capturing the rocket. This moment was so complex, it's worth examining other details. For example, the mechanism's arms could only close after about half the rocket had already passed. In addition, since the arms were designed to touch the rocket, they were covered with a type of sponge, so they wouldn't damage the rocket. And the rocket has an area already prepared for these intentional touches without suffering significant damage. It's an impressive, well-designed system. Another thing that's worth analyzing, and that was extremely critical for this landing to be successful, was the rocket's orientation. Airplanes have 3 imaginary axes on which they move, namely the vertical axis, the lateral axis, and the longitudinal axis. Rockets, despite their cylindrical design, also have these same well-defined axes. And during Super Heavy's long return to the tower on Earth, its correct orientation regarding its vertical axis or axis of rotation was something extremely important. That's because the maximum margin for the landing legs to make contact with the platform was very limited. If the rocket came in with a rotation that slightly deviated from that narrow margin of just a few degrees, the landing legs would miss the target, and most likely, the rocket would land and end up resting on the grid fins, which could be a problem. This landing demands unmatched precision and complexity, unlike anything the aerospace industry has previously attempted. The most amazing part is SpaceX succeeded on its first attempt. Everything went as planned. There were thousands of failure points, things that could have gone very wrong. Just in that moment of landing and capture by the mechanical mechanism, the Super Heavy could come in with a very high vertical speed, and the arms might not be able to close in time. It could come in with a very high horizontal speed and collide with the Tory. The arms of the Mechazilla mechanism could close too early before the booster arrives. Among several other catastrophic scenarios that could have happened, this successful landing shows how complex and difficult rockets are, and how talented the people who designed and work at SpaceX are.